Hi, and welcome back to another fun and exciting hour of BCIT, TTED, 4060 electronics as we talk about our audio projects. And when I say hour, maybe it's less if you're running this at 200% speed with the closed caption turns on. Maybe it's a bit more if you've got to go back and decipher some of what I've talked about. So anyway, in the last couple of videos, we've taken a look at some of the audio projects and how to breadboard them. And we took a look at the Erie project, which I have breadboarded right in here using the TL082 op amp and the electret mic right here. And this can pick up ambient sounds. And we took a look at the feedback on the TL082 and how we were able to use that to get a 200-fold gain in the amplitude of this mic so that we could use that to drive a set of headset speakers. So not all that powerful, but enough to take that the very small signal that you're seeing right here and amplify it to the point where you can actually listen to it with headsets or observe it on an oscilloscope fairly easily. We also took a look at, well, a fairly simple circuit for wiring up the the DF Player Mini. Right down here, we've got a DF Player Mini, and there's a micro SD card pushed right in there. You will need a micro SD card to get audio out of here. And this is a great audio source. Costs about $5 and means that if you hook something up wrong and somehow put voltage to your audio source, you might end up toasting a $5 micro SD card, or a $5 DF Player Mini, but you won't toast the audio output of your phone. And we've taken a look. The diagrams for the DF Player Mini are online, and it's fairly simple to hook up. And the great thing about the DF Player Mini is that it does have an amplifier built into it, and coming off of this pin and this pin right here, you can hook up your speaker on your big bad breadboard board, or just well, most speakers that you'd have access to sitting around the shop, most small speakers, and you can hook that up and you can run that and you'll be able to play that speaker. There is a chance, however, that you want to amplify things a little bit louder, and today we're going to take a look at one of the ways we can do that. Now, before I go on too much further, I do want to remind you that the power line to the DF Player Mini is 5 volts maximum. You can actually run it at a little bit less, but you do not want to have that hooked up to anything more than 5 volts. Now, we're going to be hooking our other power rail up here up to 9 volts today. Okay, we needed to do that to get the TL082 operating because it needed that full range for the voltage. It needed to have the full 9 volts on it. And so you want to make sure that your DF Player Mini's power pin is hooked in to only a 5 volt source, and that you're not jumping from the positives from the 9 volt power rail on your breadboard down to the 5 volt rail on your breadboard. Since there's only one pin going in here, you could make both of these rails 9 volts and then just run the 5 volt pin into right here. Kind of your choice, but watch out for that because there's no point needlessly toasting your DF Player Mini. You got a couple of buttons right here, and those are wired back into the control pins on the DF Player Mini, and those choose what music we're going to play and how loud we're going to play it, and we're going to use both of those today. We also took a look at the Color Organ Triple Deluxe, another circuit that you can find online with a quick Google, and our audio output from the DF Player Mini. There's the amplified output right here, but there's also what we call a line level output. And this is what you'd use to drive an amplifier, and that comes out through this blue line right here, through the resistor, in through the capacitor right here so that it removes any DC from that circuit because you can't get a DC signal through a capacitor. We talked about how the diode and the resistor right here bias this circuit down to 0.7 volts. So when that circuit comes through right here and it hits the base of the transistor, it turns this NPN transistor on and off. And when we turn the transistor on, it pulls the voltage down from 9 volts right into here, sends that back down to ground. So the signal in here, which is normally 9 volts, whenever there's a big pulse of music comes through, that drives it down, and our signal down here goes out to resistor capacitor filters, and we use that to drive our LEDs. So we've talked about this circuit in here already. We've talked about this circuit in here already. The LCD is set up for a different project that we've been using the Big Bad breadboard for. It's running off the Arduino that's mounted down at the bottom, and we've just kind of worked around it for now. And in right here, we've got our TL82 Erie circuit. Again, in a previous video, we've got a potentiometer for that, which is part of the gain circuit, so we can control that. And now we're going to take a look at the very last circuit and use that to talk about some amplification terms. And this is using a little chip called the LM386. And I think if I zoom in really closely, you can just see 386 N showing right there. And it's actually a really simple circuit. I have it drawn right down below me right here, and it's not far off the reference diagram in the data sheet. And that's something that I wanted to point out, is that the data sheet for all of these chips and everything that we're talking about here is available online. And when you learn to read a data sheet, they're actually really kind of useful. And so I just wanted to pop this up, and let me blow it up on the screen here a little bit so you can see it. And I can show you some of the things that I like to look at when I'm looking at a data sheet. Okay, so here we go. The LM386 low voltage audio power amplifier. So now, when they give you a data sheet, the first page actually is, as much as there's technical information there, there's also a little bit of a sales pitch. And that's important to you, because if you're trying to screen out a device to do a certain thing, you want to know what its features are and what its applications are. So when we take a look through here, you'll recognize some of the terms like battery operation. That kind of makes sense. Minimum external parts. This is sounding good. You can see we don't have a lot hooked up to it. First thing you come across here, voltage supply range. And you'll see sometimes they'll say 4 volts to 12 volts or 5 volts to 18 volts. And that means that you're going to have a couple of different options available on that chip. And down here you can see that there's different device informations, and they come in different packages. So we've got a PDIP chip that we're working with, an 8-pin plastic dual inline package. And that's the sort that you can plug into breadboards. When you get down to SOIC, that small outline integrated circuit, that's a surface mount chip that we'll take a look at a little bit later on in the year. And here's another even smaller surface mount format. You can see that if we were working with 3mm by 3mm chips, that we'd really be needing tweezers and all that. But with care and attention, you can do it. We're just not going to do that today. Okay, so take a look, and here's a key line right here. I just want to highlight that for you, because we talked about gain when we were talking about the TL082. And in the Erie circuit, we had to use a feedback circuit to set up the gain. And because this is custom designed for audio amplification, it's already got the gain feedback loop built into it, and it's set to 20. So gain, as you'll recall, means that if I put in 0.5 volts as an input, it's going to amplify that 20 times and try to give me 10 volts as an output. Now you're going to need a big enough power supply. It's not going to magically create voltage on its own. So that's going to run into some problems that we see later on if you try to put a 0.5 volt input into it. But if you put a 0.1 volt input into it, then it can multiply that by 20, gain factor of 20, and give you a 2 volt output, which is probably enough to drive a small speaker. Okay, and it also talks about a little trick that you can do if you want to bump that gain up to 200. Well, you can try it. We don't need to go there. We're going to run at a gain of 20 because we've already got a fairly strong signal coming in. But if you had a very weak signal coming in and you needed bigger gain, you could get more gain. The trouble is, if you take too much gain and you've got a little bit of noise, unwanted sound coming into your circuit, not only are you amplifying the music that you want to amplify, but you're also amplifying the noise. And we're going to talk about ways that we filter the noise out of the circuit so that you only get lovely, pure audio. Some of these things, as you read more data sheets, you'll get more used to looking at them and what they do. Now, because this is a fairly simple circuit, internally, that is. Quite often I tell people that chips are actually, they actually run off dark magic, and dark magic is all fire and smoke, and if you let the fire and smoke out, you've got to put it back in before the chip will work again. And that's an old electronics joke. It's not mine. It's not my fault. But this one's actually fairly simple, and it's mostly transistors. A couple of diodes, transistors, and a few resistors are all built together onto that one little integrated circuit. And so inside that circuit, you can see what each of the pins does right down here. And if you wanted to model that up in a circuit simulator like Falstad, you could actually get a model and see what's going on inside of there. So this is great if you want to come back and say, well, how is this interacting? How is it working? What am I doing when I hook pin 1 up to something? Well, you're affecting the input to one of the transistors right here. So there's interesting stuff going on right here. Here's where your main input comes in right here. And there's some neat stuff going on. I'm not going to dig too deeply into that. Then you start getting past the easy stuff. And you end up with a whole bunch of words here, but usually they have a table of contents to help you sort things out. And this is where data sheets can be really powerful. One of the things that we do like to look in here is quite often they'll have example circuits, application and implementation. How do you use this darn thing? And this is written by the engineers who put it together, so they'll use engineering shortcuts and terminologies. But reading the data sheet, if you do it once or twice a year, every time you get a new chip, or a new part, you go and look up the data sheet and you read it a little bit. After a while, they start to make a little bit more sense, or you see some words that you don't know and you Google them on the first data sheet, your vocabulary expands a little bit. And after you've done it for a couple of years, reading a data sheet is pretty useful and it makes a lot of sense. The other thing is that you start to learn where to look for things. And so right here, here is our pin configuration and functions, and you'll see this for just about every chip. It tells you what each pin is, where it's located on the chip, and what it does. And this pretty much describes what's going on right here. We've got, somewhere every chip's going to have ground, and it's going to have power. This one's power is marked by VS. This one's got an output. It's marked by V out. You'll see some strange terminologies. You'll sometimes get VS and VDD and VSS in there. And if you're not sure what they are, just give them a Google, because there are good interpretations for all of this out on the network. But you guys know what ground is, and you know what the supply voltage is. And if you're ever not sure, before you even go Google it, just take a look. There's usually a chart down here. They follow all of those good procedures that you're taught in your communications class, and they actually interpret this diagram for you and have a matching table down here. And they tell you everything that's going on right in there. Then they'll come down here and they'll tell you the absolute maximum ratings, and they'll talk about the temperatures that you can use things at. Most of the things don't really matter to a high school shop project, but they do matter if you're going to be packaging them into devices that will be sold both in the Yukon and in the Australian outback, because then you're going to be worried about a fairly broad extreme heat range. If they're only intended for indoor use, then you're maybe not so worried, but electrostatic discharge ratings, again, you're not so worried about that. But if you're making these and 1 in 1,000 of your multiple millions of products fails because it has somebody with static electricity touches it in the wrong place, you're going to have a problem. Now, recommended operating conditions, you'll find something down here. Let's see, speaker impedance right here. This is something we're going to talk about a little bit later on when we talk about our speakers and how things behave. But there you go. It's recommended for a 4 ohm impedance speaker. And I think we're going to run it off of a 32 ohm or an 8 ohm speaker. And this is just its recommended. It works with a whole bunch of different ranges, but if you want to get your maximum volume out of it, they say that's the way to do it. Your supply voltage, you need 4 volts, maximum of 12. If you've got the LM386 N-4, check your part number. Your supply range is actually 5 through 18 instead of 4 through 12. So we're running at 9. We're good in either range. There's your thermal information, electrical characteristics. Okay, now here's, you've got your output power, and they'll give it to you under some different conditions right here. Your impedance on the output, your total harmonic distortion, in other words, how much the noise gets messed up, you've got a maximum on that, and your supply voltage right here at 6 volts, 9 volts is where we're going to be running, and so we're going to have somewhere between 500 and 700 milliwatts of power output typically going into an 8 ohm speaker. Now that doesn't sound a lot if you're used to talking about 100-watt amplifiers, and we're like, yeah, well, this is a 700 milliwatt. It's not even 1 watt. We're going to talk a little bit later on about sound and sound pressure levels and why 1 watt is actually a lot more impressive than you might think in terms of creating enough audio to annoy the people around you with repeated ABBA songs. Yeah, my wife's just over there. Poor girl has been listening to me run my music tests on here, and ABBA apparently is better than my 1 kilohertz test tones. Alrighty, so typical characteristics, and down here is one that's kind of interesting. You've got voltage gain versus frequency, and if you leave the capacitor between pin 1 and pin 8 out of the circuit, it says it's rated for a gain of 20. Looks like it's actually coming in closer to about 25, all the way out to 100 kilohertz range. And 100 kilohertz is way beyond the range of human hearing. You'll notice this is a logarithmic chart, and we're going to talk about log charts a little bit later on. I know this isn't real big on your screen right now. Let me see if I can zoom in on the log chart a little bit bigger. There we go. And so we're going to talk about logarithms later on because they're used when we're taking a look at decibels and bells and how we talk about amplification and gain factors. But you'll notice on here, and you've probably seen this used looking at the coronavirus spread charts as you try to amplify things up. But you'll notice that we start at 100. This line's 200, 300, 400, 500, 600, 700, 900, and then we get to 1,000 right here. And this line is 2,000, 3,000, 4,000, 5,000, and then we get up to 10,000, and then 20,000, 30, 40, all the way up to 100,000. Now what that lets us do is that lets us have good resolution down at this end while still having a chart that fits in a reasonable size with all of these high numbers on it as well. And one of the reasons that's valuable is you can think about it when you're down at 1 kilohertz, being off by 100 hertz is a 10% error. Well, when you're out at this end, a 10% error is actually going to be 10 kilohertz, 10 times as much as the actual value was down here. So at the low frequencies, a small difference is a big thing, and at the higher frequencies, a small difference isn't that big of a thing. So when you're looking at relative values, log charts are really good, and so we're going to talk more about logarithms a little later on and how they fit into the decibels. All right, other information on here on this chart. Let's just keep scrolling down here, and you can download this. And this is what I was saying, where circuits come in really handy. Typical application, LM386 with gain equals 20. Now we're using a slightly modified system where we've added a little bit of bass boost to it, so there's 1 or 2 changes in our system, but you'll see a lot of common things between this and the Monobox circuit that we're using. One of the things that they've got on here that's just a little bit different is they've got a potentiometer on the input right here coming into pin 3, and that's so that you can actually have volume control. And what happens, of course, if your input's right here, and this is ground, and this becomes a voltage divider with half of the potentiometer's resistance on the top half and half of the potentiometer's resistance on the bottom half if you're right in the middle. And as you turn it up, your input gets closer to your input, and as you turn it down, your input gets closer to ground. So as you turn it up, it gets louder, and as you turn it down, it gets quieter. which kind of makes sense. So that's one way that you can implement volume control into this circuit. Another way that you can implement volume control into an amplifier is by controlling the feedback like we did on the Erie circuit. So this talks a lot more about the details, and you can go through and you can read a bunch more on here. It shows you how to set it up with a gain of 200, and somehow it talks about, do you want a gain of 50? There's a way that you can set it up with that. Then they've got other more obscure circuits that you can use it for and other applications. Here's one with bass boost. This one's starting to look a lot like what we're using for our circuits. Okay, so that's the data sheet, and it's got a lot of useful information in it, and it goes on for a while. But getting used to looking at data sheets and looking at some of the basic information on them is a fairly useful thing to do. Let me turn this screen off, and we'll come back to our circuit over here. There we go. Okay, so this is the actual chip that we're looking at, and we've got our schematic right here. So I'm just going to go a little bit over how I've breadboarded this together. And let me just bring this up on the screen, and there we go. Now there is our schematic. So our chip is sitting right here, and all the pin numbers are right around it. So I'll just cover off some of the key things that we're taking a look at on here. Okay, and you can start wherever you want. The key things to note is the notch in the chip is down at this end right here. So when you've got that notch right there, that means my pin 1 is going to be located right in there. Now when I was setting this up, I didn't start at pin 1 because pin 1 just looked a little complex. Maybe I had a bit of advanced knowledge having done the circuit once or twice before. I said I'm going to go for the easy things. And the easy things to me looked like pin 4 right here, straight to ground, is really easy. So I like to do the easy things first and mark them off as I do them. So I came down here and I said 1, 2, 3, 4, and 4 comes right down here, and I went down to ground. Now, although I said we're keeping the voltage separate between our 5-volt rail and our 9-volt rail, keep in mind that you've got to keep your grounds connected, okay, because our 0-volt reference is really important to keep as a standard, and that's what our ground does for us. Okay, so let's see. You can always keep the grounds hooked together. In fact, you really want to keep the grounds hooked together because that lets you make a very short jump right in there. Pin 4 is done. Now, also over in our circuit, it says pin 2 also goes straight down to ground. So that was pretty easy to do because there's pin 1, there's pin 2, and pin 2 jumps right into ground right there with a nice little black line. Okay, so as you go through, if you've got a paper copy of the circuit right there, you can start marking the easy stuff off. Pins 7 and 8 don't go anywhere. Okay, so we can mark those off as done. And of course, pin 7 and pin 8 over on this side of the circuit right there. And just take a look, make sure you didn't slide anything into those holes by mistake. And pins 7 and 8 are clear right there. So that's all good. Now pin 6 is going to be your power in. Okay, now that's pretty easy to do right there. This is pin 6, and it just comes up right over here, jumps up, and this is our 9 volts coming in right there. I've got a 9-volt battery plugged in right here. You could run that off your power supply to get your 9 volts. It's the same power supply that's driving my color organ down here. Okay, so that's pin 6 goes up to the power supply, but you'll be like, wait a minute, Jason, there's a capacitor showing right in there. Little bit of a trick that I did in here. Okay, now it doesn't really matter where that capacitor goes. I lie a little bit. It's good to have it close to where you want it to be. I actually popped that capacitor in all the way down here. It just let me put it out of the way. If you're more comfortable, you could put your 100 microfarad capacitor. I don't even know if that was a 100 microfarad capacitor. I think I just put a 47 microfarad cap in there. All that capacitor is doing, and you'll notice where it's plugged in is between your power supply and ground, is that's just buffering the power supply to keep it nice and smooth and level. And you used capacitors like that when you built your power supply circuit because you wanted to remove any unwanted ripple from the circuit and get it nice and smooth. It's really important in audio circuits, because in audio circuits, if you have any ripple or noise in your power supply, or worse on your ground line, then that's going to be amplified and become part of the audio signal that's coming out from your speaker. So that's just in there, and it's anywhere between power and ground, and it's applied in there just to smooth out the power supply, remove any unwanted noise from that circuit. So, okay, we did the easy things first. What's the next list of easy things? So looking at that, well, I've got an input coming in right here, and my input's going to come in on pin 3, and it's tucked into pin 3 right here. We've got a 100 ohm resistor that goes down to ground and joins in right there. Okay, so if you count down here, pin 1, 2, 3, I can do a 100 ohm resistor right in there. That's pretty easy to do. And right now I don't have anything else going in there. In a moment when we hook this up and we power it up and start looking at it, I am going to plug in a wire into pin 3 right there. And I'm going to break one of my big bad breadboard rules right here. I'm going to use a long wire, and that will just come down to my DF Player Mini, and it's going to pop in right here to the same circuit that is being used to drive the color organ, because that's one of the 2 output channels. Now, if you've got space on your board to build a second Monobox amplifier, you do have a left and a right audio channel coming out of this chip right here, and so you could have 2 outputs coming from here driving 2 separate amplifiers. Okay, so I'm just going to pull this out for the moment, but when I go to hook it up, let me know if I forget to plug that back in, because I won't get any sound coming out of here until I have an audio source come into the into the LM386. So there we go. I've got that hooked in right there, and then, like I say, I'm just going to put a big red circle right around here, because I'll hook that up a little bit later on. Now, the other thing that I need to do, it says I need to have the MP3 player hooked up to ground, or my output hooked up to ground. Since I've already got the DF Player Mini on this circuit, it's already hooked into ground. If you wanted to run your phone through the circuit and amplify the sound coming off your phone, you'd put that the phone's input into pin 3 right here, and then whatever your connector you're using to connect to your phone, your 1/8 inch stereo jack, the ground would just come in right here and plug into ground. So you can use this to amplify sound coming from your computer or your phone, but yeah, your choice. We're going to start with the DF Player Mini. All right, so this is something that you'll hook up a little bit later on, and so I'll just hook that up and say we've talked about it. Okay, that's an optional connection. In our case, it's already taken care of because your DF Player Mini shares a ground connection with everything else. The reason for the resistor right in here, this 100 ohm resistor, is just to provide a little bit of a load on the circuit so that you actually get a little bit of current flow through that circuit, because that will help make your amplifier at the other end do just a little bit of work to drive that line signal, and it might help keep the noise down in the line. Noise, again, is an unwanted signal, and when you've got weak signals coming in, it's very easy for them to get even, like noise is usually really tiny. Well, if your input signal is also really tiny, then you're going to amplify both of them together and your noise will sound really loud. Whereas if you can get a slightly stronger input signal, your noise is still going to be a fairly weak signal. And when you amplify them both, since you don't need as much gain, you'll amplify the stronger signal preferentially, and makes it easier to filter out the noise. Okay, now a lot goes on at pin 5 right here. And to keep things nice and neat, I didn't try to cram everything into pin 5. Now, one of the things that I see that sort of is a crime against breadboarding that a lot of people will do when they first lay out this circuit is they'll try to plug something into pin 5 right here and then jump it directly over to pin 1. The electrons really don't care, but when it comes to you or somebody trying to troubleshoot that circuit, because you've covered up the chip with this jumper in here, it makes it really hard to change the chip or adjust anything, and it becomes a hassle and a nightmare. So what I've done right in here is I've actually used an extra breadboard row. It's just one more row, and I've run one little jumper right in here, so I've got lots of space to hook everything up that goes into pin 5, and it's an easy jump to come in here with a capacitor and a resistor to get into pin 1. Okay, so right in here I've done a little green jumper, and pin 5's come out on that green jumper, and then right from there I've come down through a capacitor, through a 10K resistor, and then back into pin 1, right into here. Okay, now why we do that is you'll recall we talked about feedback circuits on the TL082. This is a feedback circuit right in here, and because there is a low value capacitor in here, the only signal that's getting pumped back through your feedback circuit is a high frequency signal. Okay, so your higher pitched audio signals are being ran through the feedback circuit, and as you'll recall from the TL82, what comes back through the feedback circuit kind of nullifies that input signal, and it doesn't get amplified as much. So what this is doing is it's letting the high frequency sounds come back in there so they don't get amplified quite so much. Now what that means in reality is that the bass, relative to the high frequency signals, relative to the treble, the bass gets amplified more. So you could look at this as a treble attenuation circuit. Okay, in other words, a treble weakening circuit. But we like to speak about things in a positive point of view. So what we've got right in here with this capacitor and that resistor, we refer to it as a bass boost circuit. Okay, we're not actually boosting the bass so much as we're attenuating, slicing back the amplification on the treble, the high frequency sounds, because only high frequencies can pass through the capacitor. Okay, now the signal comes out right here, and then we come to a 10 ohm resistor, which is a very low value resistor, and a 47 nanofarad capacitor that comes into ground right down here. And you can see these on my circuit located right over here. I've got a 10 ohm resistor. It doesn't have to be specifically 10 ohm, and 10 ohms really hard to find. If you had 39 ohm resistors and you put two of them in parallel, you'd have a 20 ohm resistor equivalent. That would probably do the trick just as fine. And then it goes through a capacitor and it goes straight to ground. And what that's for is that's for getting high frequencies out of the circuit. Okay, if you've got high frequency noise coming into the circuit that's going to be annoying or whiny, that's going to come down here. The 10 ohm resistor will keep some of it still into the circuit, but most of it will pass right through that capacitor. Again, this really high frequency stuff is just going to get drained out from right here and go straight down to ground, and it's going to make it sound better. Now, does it make a big difference? What I can suggest is that when you've got your circuit up and running, try pulling this capacitor out and seeing if you can notice the difference in bass boost. Put it back in, pull it out, put it back in, pull it out, see if you can notice the difference, and try pulling this resistor out and putting it back in and seeing if you pick up any high frequency noise. Now, may as well give it a try. Same thing, you can try with the 100 ohm resistor right here. None of these are really critical for the circuit to work. In fact, the LM386 is a good enough amplifier that you could probably make it work without this resistor, this capacitor, or that resistor. Like they say, it doesn't take a lot of parts to make the LM386 work. It is designed to make the circuit designer's life easy. Okay, what else have we got going on right here? Well, we've got our final output coming right in here. Okay, and our output comes out through a large capacitor. And here's our speaker right over here. And so our large capacitor is right in here, 470 microfarads. Now I've got a 50 volt 470 microfarad capacitor in there. If you've got like a 16 volt 470, that's going to be smaller, and it's going to work just as well. But the reason we have this right in here, and this leads out to our speaker. I've got a speaker hooked in right here to those nice Halloween colored wires. And the reason it comes out to, is hooked up right here, is because on this side of the capacitor, we've always got a positive voltage because we only have a positive supply to this circuit. And if we didn't have the capacitor here, then when we had DC coming through here, okay, when our output was sitting at 4.5 volts, we'd just be wasting electricity. It would keep flowing down here and straight through the speaker, because the speaker essentially works like a resistor on the circuit. The reason it's a large value capacitor is so that we can get our base through there. Okay, it takes a long time to charge and discharge. Try pulling that capacitor out a little later on and try running it with a smaller capacitor in there. Okay, if you've got a bigger capacitor or a capacitor you can put in parallel with it, try it with a bigger capacitor too. That bigger capacitor might work well if you're trying to drive a larger or lower impedance speaker. We'll talk about speaker impedances in just a moment. But I wanted to go through the basics of that circuit right there. Let's just clear off what we talked about right here. And there we go. We said this right here. We'll take another look at why that's important right there. And then we just run a couple wires out to the speaker and to ground. It's, of all the circuits that you've done, aside from maybe the DF Player Mini, that's going to be about the quickest one to breadboard. Keep in mind when it comes time to go and put these circuits onto your perf board and finish everything up, that you don't solder the chips onto the perf board. Remember that you always put a socket in there. Okay, remember to put the socket in there and press your chip into the socket. Okay. I say that multiple times. There's a reason I say it multiple times. It's because even though I've said it multiple times, somebody's going to solder it straight into their board, and then they're going to let the smoke out, and then they're going to have to go and desolder 8 pins and rip the chip out, and it's going to be miserable and unhappy and a waste of time. But like me, they'll remember to tell people to put the socket in next time. So I don't feel too bad about that. It's a nice thing about being in education. Everything's a learning experience. Okay, so where are we right now? We've talked about the circuit, how it works a little bit. We didn't get a chance to talk a lot about the speakers. And you'll notice that this one says an 8 ohm speaker. And let me just adjust my camera right here so I can look at some bigger things. Oh, I love autofocus. Okay, and let me just adjust this screen. I can shrink that schematic down a little bit and get it out of the way of the camera here. There we go. Now we've got a view of our camera. And so you'll notice on the back of most speakers that it will have something printed on it. Like in this case, it says 8 ohm, 3 watt. Okay, so that's going to be different from this little speaker right here, which is the one mounted on your big bad breadboard board, that one says 32 ohms and 1 watt. Well, what's going on with those readings? So if you look at the structure of the speaker right in here, we've got some wires that come in right here. They're mounted onto here, and you'll see that there's a fairly big magnet that runs right around inside here. And the whole key of the speaker is that it wants to drive this cone. It wants to make the cone go forwards and backwards. And if you push gently on the middle of the cone, you can see it move forwards and backwards, because when that vibrates, that's going to set up the vibrations in the air that are going to create the sound that you hear. Now, to make that speaker vibrate, let me just be really nasty to this poor sacrificial speaker here. It's a volunteer, don't worry. It knew it was going to be sacrificed in the name of education. Okay, it's nicest if you can do this to a speaker that's already been blowing. But here we go. Let's pull that out. And as we come around right there, you can see that these wires come in right here, and they come in to the middle right down here. And in this middle section, we've got a cloth cover on there, and that piece of cloth is covering up. Okay, we can see some of that magnet starting to come through there. Well, it's not the magnet, it's more a big piece of metal that lets some of the magnetic field transfer into right there. And let's get in here and pry this open a bit more. And there we go. That's what we're looking for right there. That little ring right there of copper magnet wire is the whole secret to making your speaker work. I'm trying to find distance from the lens where that's actually going to focus for me. Oh, there we go. Maybe if I hold that right in there. Right now, that just kind of looks like a disc, but it's actually a whole bunch of very, very fine copper wires wrapped around right in there. Now, those copper wires are attached to this diaphragm right in here, and they're sitting right in the middle of a magnetic field. So when we give that coil that sits right in there different electrical signals, we change and expand the magnetic field around that coil, because that's what inductance does. And we talked about that when we were talking about transformers and inductors in our power supply, that we're using the magnetic field strength of that coil sitting inside an already existing strong magnetic field, and the interaction between those two magnetic fields causes that coil to want to move forwards and backwards. Now, that coil is constrained by the diaphragm right here. So in order for the coil to move, it's got to move the diaphragm, and it's got to move the diaphragm out, which means you need an increasing magnetic field strength, and then it's got to pull it back in, meaning you need a decreasing magnetic field strength. In other words, to make your speaker work, you need an AC signal coming to it. Okay, now these ratings on the back right here, the 32 ohms, well, when you've got a length of super duper fine wire, okay, like we've got right here, that wire is going to have resistance. And oh, right, before I went and ripped that all apart, I meant to measure the resistance through there with my multimeter. You can take your ohm meter, and you don't need to rip yours apart, but you'll find that you actually have a resistance closer to 28 ohms. The reason it says 32 ohms is because you're working with a coil of wire, and the coil of wire also has an inductance factor in it. And inductance is something we haven't spent a lot of time talking about in the class, but it is the AC, the alternating circuit equivalent of resistance when you're trying to run current of an alternating signal through either a capacitor or an inductor or a combination thereof, because it takes a while for that voltage change to establish a current change. So depending on the frequency at which you're changing that, you're going to have reduced current flow through there. So it actually looks a lot like resistance would in a DC circuit, but it is something a little bit different. Thank you, speaker. You have served your purpose nobly. Okay, so what's different between that speaker and this speaker right here? Well, on this speaker right here, okay, we've got 8 ohms of resistance, and it's got 3 watts as its maximum power. So one of the ways we could get 8 ohms resistance is that we could have either a shorter length of wire, so that would give it lower resistance, or we could have a bigger diameter of wire, because a bigger diameter wire would, of course, have lower resistance over a long length, and that's probably what we've got right here. And because we've got a bigger diameter wire, we could carry more current through it before it overheats. And so that's probably why we've got a higher wattage speaker. If you think about some of the 40 watt and 100 watt speakers that you know, they're actually really big speakers. Well, that's because you need a really big magnet in there, because you need a bigger coil, because your wires need to be a larger diameter. Either that, or you need a much longer coil so that you've got a higher resistance in your speaker, okay, and you drive it off of higher voltage, because as you know, power, which is what a watt is the combination of your voltage and your current. So in our circuit, where we're kind of limited to, now we want to make it portable, so we want it to run off of a battery, we can't say, oh, we're going to run this off of 40 volts. But on a home stereo system where you get to design your own power supply, you could have a lot more voltage range, so you could use much higher impedance speakers and still get a lot of power out of them. Alrighty, let's wipe some of this stuff off the desk. Take a little bit of a pause right here. Good time to wet your whistle. Refresh, think about what we've gone over, and let's take a look at some of the things that we're going to do to troubleshoot this circuit. Okay, I've got my DP Scope SE up and running right here, and I'm just going to maximize that a little bit so we can take a look at some of the things that are going on with the DP Scope. And just a minute, let me, I don't want to make that too big. And there we go, almost there. I just want to this over a bit, and there we go. Okay, so we've got our DP scope up and running right here. So plug your DP scope in, and then at the top of the DP scope, you'll see a setting that says Utilities. And if you click on the Measurements Utilities, you should get the Waveform Measurements right here. We're going to refer back to them in a little bit. Okay, and we can refer to channel 1 and channel 2 as we work right in there. And let me just bring this screen up here and zoom back in. There we go. So we can see pretty carefully where I'm plugging things in. This is my speaker wire coming in right here. And now before we do anything else, we can turn things on right here and check to make sure your DF Player Mini is working. Okay, and we had our DF Player Mini hooked up, and we've got it hooked up into a speaker down here. Oh. Oh, I've got a bunch of test tones on there. You can find the test tones on D2L. There we go. and I've got some nice music courtesy of bensound.com. It is available for nonprofit applications, and boy, if you look at my monetization stats on YouTube, this is nonprofit. Okay, so right now we've got the sound coming out right here, and it's driving this little speaker down here. We're gonna leave that running just so I know I've got music. I can always see the lights blinking on my color organ, but I am gonna take the output from one of my 2 channels right here. I'm gonna plug a wire in right there, and breaking one of my big bad breadboard rules, I'm gonna bring that down right here, and with a big ugly wire that's just gonna be temporary right here. Gonna plug that in, and now this speaker's starting to crank out some music too. Excellent. There we go. We've got some music playing along in here. Now we want to be able to analyze what's going on. And so I've got my DP scope all set up and ready to go. It's plugged into the computer, mounted in down here, and I've taken a couple of my test leads, and here's one right here. I've just put a little wire into them, and that way I can take my test lead and plug it into ground anywhere on the circuit, and that takes care of both my inputs, keeps everything nice and connected to ground for me. And this white input right here is hooked up to my channel 1 red line, and that's going to be my signal line for channel 1. And I'm going to plug in right here to take a look at my input. Okay, now if you're not at that point, and if this isn't working for you so far, go ahead and use that to check and make sure that you are getting voltage right here, that you should be getting 9 volts coming in right here. In fact, use a multimeter to do that, because power supply is one of the big things that's going on. Okay, now I'm just going to tell my DP scope to run right here. Okay, now the DP scope is running, and you can actually see the audio coming in right here, and the numbers are updating on the waveform measurements. And right on here, channel 1 is set up at 0.5 volts per division. Okay, so 0.5 volts per division right there on channel 1. When the music stops, as it has right now, you can see it's basically sitting at 0 volts. Okay, now just ignore channel 2 for right now, because we're going to use channel 2 to take a look at the output. I want to just take a moment to take a look at the input right here. I'm going to replay that song right there. Oh, not that one. Okay, so our 0 volt line is right along here. So if I just stop this for a moment, this is our sound signal coming in right here, and you can see it's not going very high or very low above that 0 volt line. We're at a 0.5 per division scale, so our maximum peak right there was 0.5 volts. Oh, we got a little over positive 0.5, and we got a little below that right there. So what we want to do is we want to take that and amplify that so that we've got enough power in there to drive a speaker. And to take a look at what that amplified signal is going to look like when I come out, I'm going to take my channel 2 and I'm going to plug in right here on the downside of the capacitor. Okay, and I'm going to run that again. And now I've got blue and red lines bouncing all over the screen right on here. Okay, and now I'm just going to press stop on my DP scope so that I can take a look at what's going on. Okay, now you can see that these 2 lines, I've got the same scale set up for both of them. You can see that they both track each other pretty accurately. So when the sound is going up right in here, this one's going up in here, you can see these little variations right in here are replicated as amplified variations of the sound right out here. And then we come down on this side, and all of our tiny little input bumps right here are amplified as larger output bumps right here. And you can see that our peak voltage right up here was 0.51, 1.52, about 2.5 volts, and our lowest voltage was also down about 2.5 volts. Now this is where the waveform measurements come in here. They're quite nice because the computer does all these calculations for you, and it's a little more accurate. There we go. Our low was minus 2.79 on the screen. Our high was 2.6. I sound like the weatherman. The other one we want to take a look, there's our amplitude. We had 5.39 volts between them, and our ACM RMS across the screen was 1.3 volts. And as you recall from your power supply, your AC RMS voltage, okay, is sort of the equivalent that you'd have if you had a DC signal coming out. And it's one of the key figures that we can take a look at to analyze the actual power coming through this waveform. On channel 1, which is our input, we were at 164 millivolts AC RMS. And on channel 2 coming out here, we're at 1.33. So if I take my calculator and I say, let's see right here, ooh, big calculator screen, 1.33, enter, 0.164 divided by, that's telling me I'm only getting a voltage gain of 8.1 on there right now. Again, there may be a little bit of measurement error going on there. Not quite the gain of 20 that we were looking for, but you can definitely see there's more voltage in the blue line than there is in the red line. Now, this works great up to a point, okay? As I was saying, we've amplified the input signal because it's larger when it comes out as the output signal right up here. We're able to control the strength of our input signal. So I'm going to go back and I'm going to play that again. Okay. Oh, what just came loose right there? And if I hold down the button here, oh, let me run the oscilloscope. I'm going to increase the audio. Hold that button down for a little while, and that increases the volume here. Let me take a look at what our output's doing right on here now. Now, I'm just going to quiet it down because it really sounds awful right here. I don't know if you can. I'm just going to quiet that right down for now. Remind me when I say it's not working that it's because I turned the volume all the way down. And what you'll see is that our peak voltages are starting to go up, and we're starting to hit some peak maximum and minimum ranges. Now keep in mind we've only got a range of 0 to 9 volts that we can drive this thing on. And then you've got a little bit of overhead voltage loss in the speaker and all the components around it. So if we ask it to amplify too much, the chip can't magically create that voltage for us. So we end up running into flat spots right up in here where we're asking for a higher voltage on output than the speaker, than the amplifier chip has as an input. So if I put in, here's my input right here, it says our maximum input was 343 millivolts. Okay, well, if I take 343 millivolts, and even if I only amplify that 8 or 10 times, that's going to come out at more voltage than that chip's going to be able to provide. So it's going to come up and we're going to get this flat top on our signal. Now, music is a complex signal, so it's sometimes a little bit hard to see that in action with a complex signal. So I've provided some test tones for you, and you can download them from D2L, or you can create your own test tones. There's a number of different pieces of equipment that allow you to do that. But let me bring the volume back up on here. Okay, and there we go. We've got the audio coming through right there. And now I'm going to switch to the next. Okay, so here we go. We've got 250 hertz sine wave. Let me take a look at what our input looks like and what our output looks like with that. Oh, look at that. Oh, that's because I'm hooking the ground up. It's amazing that anything happened there at all. There we go. Let's just stop that and look at that. Horrible, horrible looking amplification signal coming out. Here's our output coming right in there. Now, what you'll notice on here is that our input goes up right in here, and because we're presenting such a clear signal, we're actually getting like 1 whole volt of input right here. And our channel 2, our output, just, the chip can't amplify that amount. And you can see down here, it's coming down low. We're getting some low amplification, but we've got these big flat spikes right in here. That's just because we're trying to amplify things too loud, and we're getting a horrible amount of noise coming off there. That just doesn't sound really good. We've got some other test tones that run at higher frequencies. Let me grab my output right here. And there we go. At 1 kilohertz, you can see that our output signal's not quite as high. And we're getting pretty close, but again, we're maxing out right in here. The speaker and the capacitor and that only have certain characteristics coming right through in there, so we're not getting as much sound from that. Let's try. Here's 2 kilohertz. Same thing. Let's try. Oh, that one looks interesting right there. Oh, there's so much data coming in that the chip's running really slow. Now you can see a higher frequency right in here. And, we're actually getting not bad amplification on there. That does look like we've got some gain going on in there. And we're not maxing out at the top. Interesting, there's some low frequency distortion coming through right on there. And you can see that this signal coming right in here, that's not part of our input, or at least it shouldn't be. So maybe that is the result of some fluctuations in our power supply. So that's not really a pure output signal. And audiophiles would take a look at this sort of signal and say, your your output should be a pure amplification of the signal that you're putting in with it. And they'd say, well, are we having this problem because of the MP3 encoding on the DF Player Mini, because of the output circuit on the DF Player Mini, or because of the amplification circuit right down here and the chips that we've got hooked up to it? So you can see some interesting things running when you do that. Let's find another interesting test tone to try. Oh. Okay. So here we go. This is a sawtooth with 2 different frequencies put into it. And so this is intentional right here, that we see this low frequency coming down right in here. And that repeats over and over and over. And then it's got the high frequency laid over top. And instead of it being a sine wave, it's this kind of sawtooth pattern right in here. So that's why you've got that more of a buzzy type sound to it. Thank goodness I only made them for 30 seconds. So again, we've got our amplification on there, but we can see that coming in right there. And it looks like that was actually amplifying okay. Now, if I was to jack the volume on that and be, get some really annoying sound on there, again, our input signals would go too high, and we'd see these start to max out at the top. So if you see things starting to max out at the top, then you're getting into some problems there. here's a sine wave with 3 notes on it. And I'm just going to stop that. I'm going to run it right there. And wow, I'm not seeing that very much at all. Now, if you want a better analysis of what's going on, you can ask DP Scope to show you the frequency spectrum, and you can run it right here, and you can press stop at some point. There we go. And so what it's doing right there is it's analyzing the 2 input signals. And instead of it showing us with time across the baseline right in here, it shows us with frequency across the bottom and the strength at each signal in there. This is called running a Fourier Transform across here. And so it's recording the signals in what's called the time domain, but it's showing us to them in the frequency domain. And it's really useful for analyzing where your signals are. And in here, wow, that bass, remember we said we had bass boost on this system? Well, the bass is coming out super strong, and our other 2 notes are almost invisible right in here. So maybe our bass boost is a little bit too strong. This is one of those cases where I'm just going to reach in here and try pulling out that resistor and disable the bass boost circuit. And let's see what that does. I'm going to run that. Okay. And let's run this again. Wow. That's looking quite a bit different without that circuit right in there. You can see that we've actually got some signals coming in here that aren't being replicated, and the system actually is creating some output harmonics all on its own that we really don't want in there. So by running test tones through your system, you can not only hear, but with your DP scope, you can see differences in the circuits. I'll run that again. Oh, just a minute. No, that. So I should see 5,000 and 504,000 on there. And if I take a look right in here, I've got 1 kilohertz per division. So there's my 500. And then that's 1 kilohertz, 2 kilohertz, 3 kilohertz. There's my 4 kilohertz input spike. But if I turn that on, oh yeah, there I've got my output coming out there. It's just not amplified quite as much. My output, though, was creating some harmonics of its own right in here. So we do have a little bit of distortion in our noise output. So when you're playing around with amplifiers and you're trying to test to see, do I have a great amplifier or just a good one, try injecting some signals into them and using the frequency domain on your DP scope as well as the regular time domain, you can actually see if your outputs are as good as your inputs. So there's some really neat stuff going on in there that allows you to analyze what's going on. Now, some of that is, boom. There was a lot covered in this video, and there are people who've expressed this in different ways, and the more different ways you hear it and see it, I think the better you're going to understand it. So I have gone out and found a few internet resources that I do like. Some of them I've linked to them on D2L. Some of them have been suggested by students. So if you come across a great resource, then go ahead and please feel free to mention that to me. What I wanted to do was bring up my LM386 data sheet right here. And let me just add one more window capture on here. And window capture, LM386 speaker amps. Sure, there we go. And okay, so I've just switched over to the web right here, and a website that I found that's actually got some really great explanations right on here is jeffthegraygeek.com. And anyways, he has some neat descriptions on here of understanding what amplifier power is and how to calculate it. And so if you're interested in more about audio and you want to build some nice audio equipment and understand what's going on at a fairly fundamental level in audio, and why when somebody sells you a 40-watt speaker, some 40-watt speakers are going to cost $5, and some 40-watt speakers are going to cost $500. And he's going to talk to you about why some of those might be a good deal and other ones might not be a great deal. So he's got some great explanations in here about amplifier power and how amplifier power works. Here's the clipping that we talked about in there that where we were running into a problem because we were hitting our peak voltage. And you'll see him and a lot of people talking about decibels. And that's the last thing I want to wrap up with, because you're going to run into this from time to time. It's related to those logarithms that I was talking about. And it's actually fairly simple to understand at a mathematical level. There's some practical, interesting things that happen as you try to understand them as well. So let me just wrap up by moving some of this out of the way, and let's go back to the display right here. We can actually shrink all this back down. Okay, there we go. Got my screen in here. And so what's it all talking about when you see somebody talk about a decibel? I referred to this earlier on when I was mentioning logarithmic scales and why decibels matter. On our TLO82, we had a gain of 200. So what that means is that our output, so this is our gain or amplification, okay, is 200x. So in other words, our output voltage A times not a big deal. Now, quite often when we're doing amplification, if we've got a small signal and we amplify it a little bit, we really care about that little bit. Like when we were looking at that logarithmic chart, we cared about the little bit because a small error in the little bit causes a big error in the big bit. Another way to look at it would be to say, you know, to a student, $10,000 is a lot of money. You know, 30, 40 years from now, when you're looking at closer to retirement, probably $100,000 is going to be a lot of money, and it's going to mean the same to you as $10,000 would right now. Now, if you happen to do really, really well on your investments, or marry wisely or whatever, come up with a big educational consulting company, bought some Apple shares, whatever, maybe you'll become really wealthy, and to you, $1 million will be a lot of money. Or perhaps, you're related to Bill Gates, and somewhere in the neighborhood of $1 billion is a lot of money. Now, when you're down at this level, $1,000 makes a big difference. But when you're up at this level, you don't even stop to pick up a $1,000 bill. In between here, well, yeah, you probably would pick up a $1,000 bill, but it's not that big of a deal. Down here, $1,000 is a really big deal. So what we try to do is we try to express these not as absolute values when we're looking at things. I mean, obviously with money, that's a little bit different, but in our signals, we try to express them as relative to the input signal. And that's where we use gain factors. Now, gain factors start to spiral out of control really quickly. So if you have a gain of 10, okay, and a gain of 100, then you might have a gain of 1,000. Okay, what we actually do is we go back and we use the log function and we say 10 equals 10 to the 1, 100 equals 10 to the 2, and 1,000 equals 10 to the 3. Okay. Makes sense. We've used that for resistor color code, capacitor numbering. Why wouldn't we use it here? So each of these numbers right in here, the log of the amplification, is a bell. When we talk about a decibel is, deci means 1/10 of the bell. So when you've got a gain of 10, okay, that is going to be a 10 decibel gain. If you've got a gain of 100, that's going to be a 20 decibel gain. And if you've got a gain of 1,000, we're going to call that a 30 decibel gain. All we do is we take the log, we multiply by 10, and it gives us our decibels. And it's just telling us how much stronger the output signal is than the input signal. And there's more complex math that goes around on this, and it works out really great for 10, 100, and 1,000. You have to do a little bit of math to get 200 and 400 and 578 or whatever number you're going to pull out on there, but it all works out. And what it does is it takes exponential gain right here and expresses it on a linear scale, because humans think much better in linear terms. So we tend to use these decibels for gains, even though they actually indicate massive changes in the signal strength. And that matters because our perception of sound is not linear. Well, our perception of sound is linear, but the actual energy in the sound has to be exponential. In order for us to have something sound twice as loud, the signal needs to be 10 times and 10 times right there, that would be 10 decibels. Okay, because 10 is 1 bell, 10 to the 1 gives us 1 bell, 10 decibels louder. So you need to get a 10 decibel gain to make something sound twice as loud. So in order to have it sound 4 times as loud, then you need to get a 20 decibel gain, which means that you need a gain of 100 in your circuit. So in our circuit, we've got a 1 watt amplifier, okay? Well, in order to get something that sounds twice as loud, you would need a 10 watt amplifier. And if you went all the way up to a 100 watt amplifier, it would only be creating 4 times as much sound as that one little circuit that you've got right there. Now, a 100-watt amplifier doing 10 watts of amplification is probably going to sound a heck of a lot better than a 10-watt amplifier doing 10 watts of amplification, because the 10-watt amplifier will be operating at its absolute limits to provide you that level of sound, whereas the bigger amplifier will be operating, much closer within its operating range. It'll stay cooler. There'll be less distortion in the power supply. So having a more powerful amplifier would allow you to run well at lower levels. For instance, down here, when we're driving 1 watt coming out right there, that thing was floored, and you could see the errors that we were getting in our output when we looked at it on the oscilloscope. A 10-watt amplifier would probably not be having that kind of problems. So anyway, some very interesting things happening right in there. The other place you'll see decibels being used is in relation to audio in your shop. And when they talk about audio in your shop, they tend to use what's called dBA. And the A is the A-weighted scale. And that takes into account the fact that the human ear doesn't hear all sounds equally. So if I give you a 500 hertz sound, a 5 kilohertz sound, and a 15 kilohertz sound with the same sound energy, one of them is going to sound, well, considerably more annoying than the other. It's going to sound louder because our ears are going to vibrate more naturally at that frequency, and our brain is going to pick up that signal more easily. And it tends to be within about the range of human voice that we're more sensitive to pick up the sound. You can ask, did our voice evolve to match our ears, or did our ears evolve to match our voice? Who knows, but they kind of match in there. So when you're looking at shop equipment, low frequency sounds aren't quite as damaging as sounds that are in that range of the human voice, and the high frequency sounds, which can be really bad, actually need to be really high energy, and they tend to be to cause long-term lasting damage. So you'll see it used in the shop, and it's a dBA weighted scale, and it's all referenced to a very, very low signal strength, which has been described as the sound in a perfectly quiet room of a mosquito flying a meter from your head. Okay, that's their reference sound, and so that would be listed on the decibel scale as like 1 decibel, and then everything that goes up from there is an exponential increase in sound energy, but a linear increase in how the sound sounds. Yeah, that's why I left that for the end. It's not really examinable content, but we do need to touch on it because you're going to see these terms, decibel, being used right in here. And like I say, they're not that complex. They are worth taking time to sit down and figure out, but you're safe. They're not on the final. We're going to talk more about your circuits, and we'll get you all prepped for the final when that comes around. Alrighty, folks. There we go. Now, once you've got your circuits all put together on the board, you can put them together one at a time on your board. You can put them together, all at once and get that all worked out. Then what you're going to want to do is you're going to want to take a look at starting to transfer them over to your perf board. And that way you're going to be able to permanently have a nice, record of everything that you've done in here. Even though we weren't able to make printed circuit boards this year, you're going to be able to hook them up. I maybe went a little overboard on this circuit. You can see I've done a second color organ down here. In your kits, I haven't given you the parts to do that. I rewired a couple things down here. Instead of using big buttons, I use small buttons. You don't have to change that up, but you've got the small buttons and they work fine on this board. Just think about how you want to wire them in. One thing you probably do want to do if you're going to do this for a permanent installation is, instead of trying to just plug wires into a breadboard, what you probably want to do for putting your speakers on here is using some of our little amp connectors and a couple of header strips right on here, so you can plug your speakers in right there. You can plug your power supply in right here. I added a little circuit right in here on this board so that I can run everything off of one 9-volt battery. I gave it an on-off switch right here. So if you look closely right in there, you can see that my ground line comes in right here and just jumps right into my ground line, jumps into the ground line on the other side. My red line comes into this side of the single pole double throw switch. When I throw the switch into this position right here, okay, you can see that now the middle line right here gets connected. That middle line comes up right in here, and I run it through a diode right here before I bring it back out to the red right here, just in case somebody ever hooks a battery up backwards. It won't damage anything in the circuit. You don't have to do that, but if you've got a diode, you can do that. You could also take that diode and hook it directly into the positive line if you wanted, move that over one. To get my 5 volts for powering the DF Player Mini, I have a 7805 voltage regulator in here. These are a fixed voltage regulator. Comes in right here, and you can see on that middle line where the voltage comes in right here, I've bent that lead right down in there just so that it skips over one hole right in here. Let me turn that off so I don't short anything out. You can see that lead right there. So on your 7805, you've got input. Your middle one is ground. You can see that's tied into the ground line right there. And then I've got my 5-volt output right there. And my 5-volt output, I take right off of the back right here. It comes in right here, comes around this side, powers up my 5 volts on this side, and then I add a capacitor on this side just to smooth that out, because you should always have a capacitor on the downside of your regulator. In fact, I got really enthusiastic and added another capacitor right in here. I'm not sure why. 2 capacitors better than one? One's better than none. Anyway, so I've got my 9-volt line coming in right here and ground. I also added a couple of capacitors down a little further on this line. I just had a nice place to put them in right there, and that serves the same as the capacitor between the C4 on the amplifier circuit that we were talking about earlier, just to make sure we have a nice buffered, smooth power supply for the circuits. Tucked away in here, I popped my Erie in right here, and I left a little header strip right in here so that I can plug in some headphones anytime that I want. I've got my DF Player Mini in there. I switched the buttons up. Now I went to town a bit on making it so I could switch which input goes where. So I have different inputs coming to different switches. I made it so that my Erie, let me turn this on, and my Erie can actually drive the, there we go. I'm using the Erie to drive the color organ right here. So if I go, woo, there we go. Look at it all light up. If I turn on my other circuit and play some music, let's find, is that still live? This is a 31 Hertz sine wave. Oh, 31 Hertz is pretty boring. Oh, there we go. Copyrighted music. So that is being played on this speaker and picked up by the Erie over here, and you can see that if I quiet that down, that my Erie goes a little bit quiet as well. So anyway, there you go. You can mount that up on your board. If you need a couple switches, see me about that. You don't need to do a second Erie or a second color organ. I just did that because I was having a fun Sunday afternoon soldering things up. And also tucked in here, I've got my, so there I've got my Erie, there I've got my DF Player Mini, and here I've got my amplifier circuit, and I've got an output speaker right on here. So if I turn this off, turn that off, I can pop my SD card out right there, slap my SD card in right here, and Turn that on. And there we go. I can use audio from here to drive that directly, or I can switch it back and forth and use it to drive that. And I'm going to turn that off before YouTube calls me up on a copyright complaint. Alrighty, folks. Like I say, another hour-long lecture that only took 90 minutes. Hope you have fun building your audio circuits, and yeah, check out that Jeff the Grey Geek website. It's pretty good.